All right, kiddos, let's take a look at that apparatus that the professor was talking about in the videos. So right here, this is an evacuated tube. We've got a filament, right, that's heating up, releasing electrons, and then this plate is a positive plate. And so those electrons are attracted to it, but there's a hole in the middle and those electrons can go straight through. Right, those electrons will go through, and if the electrons were acting like a particle, they would go through and then they'd randomly scatter, making a smudge on this screen over here. But the professor noticed that as you turn up the voltage, these electrons go faster and faster through this hole right here, and they actually start acting like a wave. All right, and we know they are acting like a wave because you see a regular interference pattern, right? A distinct series of dark and light spots with a central maximum. Okay? And as the voltage gets higher and higher, that means the electrons are going faster and faster, and the wavelength is thus getting smaller and smaller, producing a tighter interference pattern, which is exactly what we would expect if light or if something was acting like a wave. Okay, and so at certain speeds, the de Broglie wavelength is such that an electron can act like a wave because the aperture that it's being sent through is on the same order of magnitude as its of width as its de Broglie wavelength. Okay. All right, now let's take a look at Schrodinger. In 1926, Erwin Schrodinger provided a realistic quantum model for the behavior of electrons. So if we're looking at electrons that are acting like a wave, we need to be able to make predictions about where those electrons will be at any point in time. And that's hard to do because we can't really see electrons, right? We can see evidence for them, right? They create an interference pattern when they hit a phosphor target or something like that. We can see evidence for them based on a charge accumulating, but can we really know the location of a single electron? And that was the work of Schrodinger. So he suggested that a wave function, and this is its abbreviation right here, the Greek letter phi, I think is what it's called, which represents the intensity or amplitude of a wave, and that can be used to find the probability that an electron will be found at this position. All right, so this is called a wave function. It's a probability density of where a wave would be. So if you take that probability density based on the electron's position and time, absolute value, square it, multiply it by the position, that the region in which it could exist, you get the probability of finding that particle. So again, this is the probability density. This is the region in which you're looking for that particle or in which you want to see if it's existing, and then you get that probability. All right, for this, there's something called the Copenhagen interpretation of Schrodinger's theory. So when diffracted, a photon or electron is everywhere on the screen until it is observed and measured. Okay, so this is a common conceptual aspect to quantum mechanics that quite a few people know about. So an object at the quantum scale is only isolated to a position at the point when it is being observed, right? It is only that then, when it's being observed, that the wave function, right, the probability of an electron or a photon to be at a certain place collapses. And that's when the particle is detected at a certain location. Okay. Schrodinger made a joke about this interpretation. He's like, it was kind of funny, but a lot of people use it as a real description of the Copenhagen interpretation. His joke was that, right, if nothing is real, even though it's observed, then if you take a cat and you put it in a box with some poison, and that poison, it was in a vial that could break at any point in time and kill the cat in the box could be alive or dead. And we don't know if it's alive or dead until we actually open the box and find out if that vial has broken and poisoned the cat. So all the possibilities are there, until we make an observation. Right, we don't know what's going on until we look inside the box. I just want to show you the full version of Schrodinger's equation. So we've got Planck's constant, we've got position, time, we've got the that psi, probability density. This is a partial differential equation, and once you take that class, you'll be able to solve a Schrodinger equation and take a full college level quantum mechanics class, which is pretty cool. All right. Albert Einstein was skeptical of quantum mechanics and that Copenhagen interpretation of Schrodinger's theory, and he famously said, "I can't accept quantum mechanics because I like to think the moon is there, even if I'm not looking at it." All right, so based on this idea that a particle, or that something could be a particle or a wave, and that it only exists in a certain state once we choose to observe it, the Heisenberg uncertainty principle was developed. And it's based on that particle-wave duality, and it says that we cannot clearly divide physical objects into either particles or waves, right? So it says that it's not simultaneously possible to measure an object's position and momentum with indefinite precision, right? And this is a fundamental property of nature. Okay, so let's take a look at the Heisenberg uncertainty principle as an equation, right? So we can't measure an object's momentum or its position simultaneously, just like an object can't act like a particle or a wave at the same time. It's either acting like a particle or a wave. So the equation is, here, I'll not do green. I don't know why I'm in green right now. Erase. There we go. Let's do purple. Uncertainty in momentum times the uncertainty in position must be greater than or equal to Planck's constant over 4 pi. Okay, so that's the Heisenberg uncertainty equation, and these deltas represent uncertainty in. Okay, so you take the uncertainty in an object's momentum times the uncertainty in position, and it must be greater than or equal to this constant. Okay, you can also have this written in terms of energy. So uncertainty in energy times uncertainty in time must also be greater than or equal to Planck's constant over 4 pi. So those are the Heisenberg uncertainty principle equations. This momentum is just what we expect it to be, mass times velocity, or you can insert the equation for the momentum of a photon from the part A of this lesson. All right, so let's take a look at what this means, right? If you're really sure about how fast a particle is going, you've got really small uncertainty in momentum, right? You're really sure about the momentum, the mass and the speed of a particle, right? You've got small uncertainty of momentum. And what that means is that you must have really large uncertainty in that particle's position, because the product of these two uncertainties must be greater than or equal to Planck's constant over 4 pi, right? And similarly, if you're really sure, right, you have a small uncertainty in a particle's position, that means you must have a really large uncertainty in that object's momentum. Okay, so you can't know the position really, really well and the velocity of a particle really, really well. You either know one thing or another really well. Okay, so that principle was discovered by Werner von Heisenberg. He discovered this in 1927. He was 26 years old, you guys. He was one of the founders of quantum mechanics, and a famous quote from him says, "The atoms or elementary particles themselves are not real. They form a world of potentialities or possibilities rather than one of facts." Okay, which is crazy because in science we're all about facts, right? But when we're in the quantum world, we're about probabilities. What is the probability that something is at this location or traveling at this speed? All right, so let's take a look at the connection between de Broglie and Heisenberg. I think this is supposed to be an S. Whoopsies. All right, so if a particle acts like a wave, then it has a wavelength that's equal to Planck's constant over its momentum, right? De Broglie said that. Okay. If a particle is acting like a wave, we know, as a result, that we know the momentum with high certainty. I'll write out with high certainty, right? Or you could say that low uncertainty. As a result, we don't know that particle's position very well. We don't know its position well. So if a particle, like an electron, is acting like a wave, then we know it has a wavelength, right? We know the mass of an electron. We know the potential difference it's being accelerated through. We can calculate how fast it's going and what its momentum is, right? Put that under Planck's constant and we can know its wavelength, right? If we can calculate its wavelength, we know its momentum very, very well, right? A very small uncertainty in momentum, right? What that means is that we don't know its position very well. Right, so when we see this interference pattern, like we saw in the video, there we don't know the position of a single electron very well, but we have some regions where an electron has a high probability density of being, right? There's a high probability of that electron being here, being somewhere in this circle, or being on this circle. Okay. All right. And I've got some quantum cartoons, like you should.